So our next speaker now is Emma Brunskill. So she is an associate tenure professor in the computer science department at Stanford University. Her goal is to create AI systems that learn from few samples and robustly make good decisions. She was previously an assistant professor at Carnegie Mellon, and her work has been honored by a number of early faculty career awards. And she also serves in the International Machine Learning Society Board, the Khan Academy Research Advisory Board, the Stanford Faculty Women's Forum Steering Committee, and previously served on the Women in Machine Learning Board. So please help us welcome Emma.
Working. There's a small square. This one? Thank you. I'm delighted to be here. So I thought I'd start off to talk a little bit about how I ended up, and my lab end up doing the work we do. So when I was a PhD student here with Nicholas Roy, I was fascinated to learn about these ideas for how we make decisions under uncertainty. And of course, now we know reinforcement learning as something everybody talks about. It's one of the huge enablers of ChatGPT. But back then, I'd go to a talk, there'd be maybe 30 people if I was lucky. One of them would be Rich Sutton. But I found the ideas completely incredible of thinking of how we could learn autonomously to make decisions. But at that point, most of the people that were doing this were roboticists. And I think that's because that was one of the few places where we could really instrument systems and actually have them make decisions and learn from data. But at the same time, I was really interested in thinking about other ways of making impact on society. And I think, in fact, many people struggle with this, of loving one type of technical idea and then finding their heart sort of being pulled by other forms of applications. So this is an example that Bill and I, who you'll hear from soon, and Sumani, who was a wonderful master's student, worked on together at MIT. The MIT Public Service Center was incredible at allowing us to think about things like information communication technologies for international development. But this work was much more focused on systems and HCI. And while I was really excited to be part of this work, it wasn't the same sort of intellectual fascination that I had. So when I finished my PhD and went off to do my postdoc at Berkeley, I started thinking about how I could try to combine my two interests. And I started thinking a lot about education. In education, we have these sort of closed-loop systems where we're making interactions and doing interventions, and hopefully, the student state is changing over time. They're learning something. And in fact, this also has an incredible history going all the way back to AI, its beginning of thinking of how we can use AI to augment education. And at this point, there'd been many decades of people wanting to use AI to try to enhance education, but it wasn't clear yet that we've seen a lot of success. But I felt like, starting in the sort of 2010s, that maybe this was the time to revisit this, because clearly the need was there, and maybe we're starting to be at the point now where we could instrument things and start to learn really what works and use AI to better help education. So what I'll talk to you about today is some of the applications and a few anecdotes about how we've been thinking about human learning and reinforcement learning. And I'll start with an example from early in my assistant professorship. So this is a game called Refraction. It teaches kids about fractions through what else? Splitting laser beams to feed spaceships. It's a really fun game. It was developed by my colleagues Zoran Popovic and some amazing students at University of Washington. The only problem is people don't play it for very long. So this is an optional game on the web. People play it for a little bit of time, and then probably Facebook, or these days TikTok, gets more exciting, and people stop playing it. And of course, if you're not playing it, you can't learn from it. So they started talking to me about whether there might be some sort of personalized way that we could sort of develop this sort of game to students to help them persist and learn more. So how do we think of this as a reinforcement learning problem? Well, you can think of there being all these different types of activities that students can do, and what we want to do is to condition on the context to figure out what works when in order to help achieve the long-term educational goals. So you might imagine here that we sort of capture the state of the student, where they're clicking, what they're doing, and then based on that information, we give them different next activities. Now, if we were framing this as a normal reinforcement learning problem, we would think of there being this beautiful closed loop system where, like sort of the Atari results or robotics results, we actually get to interact in real time, observe what works, and then change the system before it's shown to the next student. Unfortunately, in education and healthcare and many other areas, this is really hard to do. There can either be logistic constraints or safety constraints, which means that we don't want to experiment and accidentally not teach anybody fractions. And so what we'd like to do in these scenarios is to leverage our historical data and figure out what to do. Now, this has also been something people have thought about for a long time. They've thought about how could we leverage historical data and use sort of trial and error information to figure out how we could do better in the future. So in this case, my colleagues were willing to gather some data which had some amount of variability, randomness, because they really weren't sure that the best way that they were doing it right now was the best. And so what we wanted to do is to leverage sort of the history of offline reinforcement learning, which has been around since the start of reinforcement learning becoming a computational discipline, and think about what to do. So the first thing we thought of doing was sort of just building a model. We could build a model of how the world works, and then assume that's how students actually learn, and then teach them under that artificial model. So this is a common approach. This is sort of model-based reinforcement learning. And then we tried it. So here we have on the x-axis just a number of different ways of modeling students. You might notice all of these are really small models. And on the y-axis is the performance of those models. So this is not overfitting. This is a held-out test set. And as you might expect, human learning is pretty complex. Even with a 20-state tabular MDP, we can't capture it all. So it just gets better and better. But then what we did is we took those and actually put them through the machinery of computing a good decision policy. And this is pretty easy because these are pretty small models. And the problem is, even our 20-state student model was already yielding a policy that wasn't as good in practice. Now, why was this? This is because all of these models are wrong. And only some of them were useful. So in particular, the middle level model here actually led to better performing policies. But we couldn't have got that if we had assumed that this really was a tabular Markov decision process. So to tackle this, we drew on some beautiful ideas that have been long-standing in statistics on how can we think about understanding the performance of a function under a different data distribution than from what you have data. So this is known as importance sampling. One of my former students who takes my reinforcement learning class was like, this is my favorite idea ever. And it's had a long-standing impact and allows us to get unbiased estimates of the performance of a decision policy. So it turned out this one project led to a huge amount of work in my own lab, where we started trying to develop robust, efficient estimators of how good a policy might be before we deploy it. And we drew on ideas in statistics and econometrics and some beautiful ideas in double machine learning. And it was really exciting for me to sort of draw on these other communities and bring these to reinforcement learning, including thinking about how we can actually develop better policies for the future. So it's also been really wonderful to see that over the last 5 years, this has become a huge area of interest as more and more people think about how we can leverage the enormous amounts of data we have in order to make better decisions. So this allowed us to win best paper awards and think about how we improve education systems. But let's think about what actually happened for that first system we looked at. Well, the first thing is that by getting rid of the assumption that the world is really a tabular MDP, we could start to look at lots of different ways of teaching students. And the first thing we figured out is that the normal way that people were using this system was actually worse than random. So you could just give activities in any order, and it would actually increase persistence more than doing it in the order that had been specified. Now, I don't say this to sort of ridicule the original designers. I say this to illustrate that we are not at ceiling in education. We are nowhere near it, and there's clear room for improvement. We also found something that we thought should be 30% better. So again, this is just our statistical estimate. And the great thing is then we did a trial with another 2,000 students, and it was about 32% better. So this is exciting because it means that we really could radically improve persistence in games like refraction, and also we could predict this in advance. Now, around this time, I started talking to some of my other colleagues in education and HCI who said, well, maybe in our new platforms, we're starting to be able to do real-time online learning. How much data are you going to need? So are you going to need, they see things in AlphaGo, they're a little concerned. They're like, we're not sure we have that many students on the planet. How much data are you going to need, Emma, for these types of systems? And of course, sample-efficient learning has been a long-standing question in a lot of machine learning. So if you came to the session this morning, you heard Ankur talk about some of the beautiful new work his lab is doing and people have been thinking about in the last few years. One thing you might not know is that even up to about 6-7 years ago, even really basic questions around how hard is it to learn to make good decisions were open, even for these incredibly small tabular MDPs where we can write everything down. And it matters in the sense that if you do this poorly, so if we use sort of like really simple strategies, some of which were used in things like AlphaGo initially, or some of the Atari games, not AlphaGo, as well as sort of very simple exploration, you can get the amount of data needed being exponential, or you make infinite number of mistakes. Now, of course, we want to do better than this, and some of my wonderful initial colleagues started trying to characterize how this scales with the size of the problem. What we showed together with some of my wonderful students is that you can do much, much better. And if you plug in some simple numbers for this, this is things like going from 10 to the 12 samples to 10 to the 6. So it really can just be enormously better. And this problem is now closed. So the reason that Ankur doesn't have to talk about this anymore is that we know what is the sort of tight upper and lower bounds in terms of the dominant order for both episodic tabular RL in both the regret case and the sample complexity case. We also provided some of the first instance-dependent results, which relates to how is it the case that some problems are just much harder to solve than others. Since I'm really interested in education, I'll just give you a brief example of how this works. One of the key insights we found is that uncertainty in how good a policy will be scales with the variance of the next outcomes. So what does that mean? That means that if after you make a decision, sometimes you end up in something that works really well, and sometimes you end up in something that works really badly, that you're going to need a lot more data to try to learn and figure out how good that state is. And so that means our hard instances are kind of in the middle. If we think about things like multi-arm bandits, which are commonly used in advertising, those are provably much easier because you only need to make one decision. If you think about a lot of control systems, like deterministic MDPs, those are also a lot easier because there's no uncertainty in the next state. There's only one next state. So this sort of sheds light on some of the ways in which sort of learning to make decisions is hard or easy. And of course, there's an enormous number of open questions. But I just want to close with sort of something that started concerning me over the last few years. So I'm inspired by education. I've also done a lot of theoretical work that I love. But I really started feeling like there was this big gap. I had some colleagues that developed some incredible intelligent tutoring systems where like you could double math performance in a year, or where in a statistics class you could learn the same amount in half the time. But these are rare examples. Most people are not using systems like this. And I started being concerned that we weren't really making a big impact on these type of educational problems. At the same time, of course, COVID hit, and we started seeing incredibly scary headlines like the worst math and reading scores in 20 years. And this was even before when we already had massive sort of inequities in education. And so I started wanting to think back about like how could we really go back to sort of more of a systems level and really try to improve education. Now, right now, there's a lot of funding and a lot of excitement around high-dosage tutoring, but it's still incredibly expensive, and we just don't know a lot about how it really needs to work. So right now, I, together with Carnegie Learning and Carnegie Mellon University, and a number of wonderful collaborators, are thinking about a new paradigm called AI-augmented human tutoring. The idea is that we'll use AI in lots of parts of the system. As students work with intelligent tutoring systems, they can also be supported by human tutors that are themselves getting help and advice from an AI coach. This would allow us to use students like high school students and others and help them become expert tutors. And so it could direct them on who to drop in with and who to have direct conversations with to help everybody succeed. Now, when we think about this agenda, there's also a lot of technical questions that come up. Things like, if you think of this as a multi-agent reinforcement learning problem, how do we deal with resource constraints? The tutor can't spend all their time with all the students. There's a finite amount of time. There's ratio questions. And we also want to make sure this isn't just helping the students that are already succeeding, but really helping all students. We also have questions around autonomy and support, We may need to think about things like instrumental variables from the econometrics community, because these are only suggestions to expert tutors who then can decide whether or not they want to use the AI advice. And finally, this is just an enormous space to optimize. If you think about the context of all the students and the tutor and the long-term goals and all the possible interventions, this is just an incredibly large space to try to learn what is the right thing to do. And there are delayed outcomes, like high school graduation rates, that we might really care about. So how do we do faster discovery of impact through things like automated experimental design and other forms of sort of Bayesian adaptive optimal experimental design? But to me, this is the next moonshot that me and my lab and a number of others are thinking about, which is how do we do AI, how do we create AI human ecosystems so we can double math gains for low-performing students and really achieve the goal of AI enabling quality education for all. Thank you.